Okay, so now that we're armed with the knowledge about equality and assignment, whenever possible, you should probably use AQ because that's the standard creation of a constant at the time you assemble your source code. So we can now start analyzing these three operators and see how they work. So we can take a look at the two files here, or we can just copy and paste this file in our own executable environment. But first, I'll just try to download the examples that we have here. So let's create new folder, and we'll call them examples. Okay, and this is the folder. So into this folder, I'll just simply download these two files, the listing file, save as, into this location. For this, we actually have an example of this code on our next page right here. So how about this? We just update. Let's remove these temporary examples of constants and copy and paste the actual memory allocation directives so we can talk about them. And we also have the examples of examples of these operators used with these variables. Okay, so in order to be able to find out how these operators work, before we start detailed examination of this sample, what I would like to do is I'd like to allow the listing, because basically the listing will show the actual value that this X variable gets when we apply different operators with these labels identifying various types of memory allocation. So let's work on the listing file, and I'll save my change, and we need to jump to Solution Explorer, and this is the name of my source file right here. So we need to right click and go to Properties. Okay, so here in the Properties we have, of course, this is assembler file, and Microsoft Macro Assembler is invoked for this. So we need to switch to assembler properties, and there's a listing file properties right here, and we need to change this the bottom part of this. Typically what we want to do is I will show you what we need to do is $target target name.lst. So it'll create the listing file side by side with the generated code. Okay, so let's take a look. I'll just click OK, and we should be able to find the listing file after building this program. So this is what I do with the listing file. Let's build. Oh, I removed a constant, but still was using it in the sample. So let's just get rid of that and close the. Okay, so we have. So here we have our constant segment, and now we should be able to build. Okay, everything looks good, and so the next step is to go to our debug results of the debug build under our project, and this is the listing file that I'm using right here. Yeah, I'm not sure why I'm using 707, but it doesn't matter. It's just the name of the project, I guess, that was changed to this name. So this is our listing file, and let me show this side by side. So in in our const segment, in the constant data segment, which officially begins at constant memory segment at offset 0, we store a sequence of bytes. We give it label byte 1, and we use byte allocation directive, and we simply take this constant data segment and throw their decimal values 10, 20, and 30. So they're stored as bytes. You can see that the listing file shows us that the result of this allocation is a sequence of these values which are shown in hexadecimal notation. So these are bytes, the actual hexadecimal bytes resulting from decimal values 10, 20, and 30. So these 3 bytes stored at the beginning of our memory segment. Array 1, which is using allocation of 16-bit integers, the size of processor word on x86 is 16 bits, and or 2 byte size allocations. So let's see, and therefore this allocation, array 1, starts at offset 3 into constant memory segment, because we already stored 3 bytes here, so the next offset is 3. So right here what we do is that we're basically given this array of 30 duplications of question mark, and question mark typically is replaced for integral values, just replaced with a 0. And so there is a repetition of the 30 2-byte size integers, each of them initialized to 0. So this question marks becomes this 2 bytes, because each byte is shown here as hexadecimal, 2 hexadecimal digits, so we have 2-byte allocation, and this 1E is the decimal 30. So listing tells us, okay, so what's happening at this offset into constant memory segment, that you're gonna get 1E, or simply put 30 repetitions of this. Okay, so this like 2-byte size integers initialized to 0, and then they're also followed by 2 integers explicitly set to 0, which is this and this. So now let's count all these bytes. So basically we have 2-byte size 30 times, so this is like 2 bytes times 30, right? So this is 60. This is 61, 62, 63, 64, plus 3, right? So it should be 67. 67 bytes. From here to here, we have 67 bytes already stored in the constant memory segment. And if we try our calculator right here and try decimal, just switch to byte, I guess, decimal 67. Okay, so this is hexadecimal 43, and this is precisely why the next memory allocation happens at the offset of hexadecimal 43, or 67 bytes into constant memory segment. So that's consistent with everything that we observed on top of our constant memory segment.